We will focus on the product and quotient properties with radicals. But in order to simplify radicals using these two properties, we first need to outline properties of radicals. So we're going to let n be greater than 1 and be an integer, such as 2, 3, 4, etc. And a and b are any real numbers. Remember, real numbers are numbers that we understand their value, so we could place them on a number line. So the following properties are true provided that the given radicals are real numbers. So we have 5 different properties here, and I'm actually going to focus just on the first one because it is a bit of a unique situation that we need to focus on. And then I want us to realize most of the time this will not occur for us. So the first property is if n is even. So that means our root is even, such as square root, fourth root, sixth root, etc. So notice that the root is n and the power is n as well. So I want you to think about our phrase power over root. So if our base is a, our power is n, our root is n. So wouldn't you think that the n's just simply cancel away and that leaves us with a? But what we have to come back to and remember is that a can be any real number, such as a negative number. So let's take this example. If we let x be negative, what is a negative squared? Well, a negative times a negative is a positive, and the square root of a positive gives us back a positive as well, which is why we need absolute value symbols here. Because the absolute value of any number, whether it be positive or negative, is going to give us an output that is positive. So for any nth root where a is being raised to the nth power, if n is even, then our outcome will be the absolute value of a, which means our outcome is positive. Now, if n is odd, then the n's do simply cancel and leave you with the base a. And you can see this in the example, cubed root of x cubed just leaves us with x. And then fifth root of the quantity y plus 4 to the fifth, the 5's cancel and leaves us with the base of y plus 4. We are going to dive into the product property and the quotient property together. Now for the nested radical property, I don't have any examples that we are going to do together. And so if this pops up in Alex, I want you to refer to this example right here, where the fourth root of the cubed root becomes the 12th root by multiplication. So nice little example right there. The 4 specific criteria, instead of addressing them as they are illustrated here, we're actually going to do this with examples. So we'll see what the criteria is as we look at each of our examples together for this video and subsequent ones. Now for our jobs, we're going to simplify each expression, but we're going to make our lives a little bit easier. We are going to assume that all variables represent positive real numbers. And by doing so, we will not have to insert absolute value bars around the simplified form of the nth root of a to the nth power when n is even. So we're not going to worry about that because we're going to say that all of our variables have to be positive. So problems 1 and 2, we're going to use the product property here, and they go together. So question number 1 is just like what we saw up above. Because our root is 3 and our power is 3. They're going to cancel each other. So this is a to the 3 over 3. The 3's cancel and it leaves us just with a. Done. Now problem number 2 is very similar, but underneath our radical we don't have a cubed, we actually have a to the 5th. So there are a few ways I want us to develop an understanding of how to simplify this. The first way is I want us to see that a to the 5th does contain 3 factors of a. So a to the 5th does have a cubed as part of it, but it also has more factors of a. In fact, it has 2 extras. So now we can use our product property and say the cubed root of a cubed times the cubed root of a squared. But as we said from problem 1, the cubed root of a cubed is just a, and then we're left with the cubed root of a squared. Now another way we can think about this is by thinking about this in exponential form. So if I think about the fact that my power for problem number 2 is 5 and my root is 3. So if we were to think about this as division, and isn't that exactly what a fraction is? A fraction is just implying division of the numerator by the denominator. We could use the algorithm, the rule of how many times does our root of 3 go into our power of 5, and the answer to that is 1. But it doesn't go in evenly, there's a leftover. How much is left over? 2. So we'll continue to practice with our exponents in this way. So next 2 examples pair together as well. We have the 4th root of 16. Now remember, 2 raised to the 4th power is 16, so that means the 4th root of 16 is 2. Done. But with 48 is not a perfect 4th power, so we need to tear this apart. 48 has lots of different factors. It has 2 and 24. It has 4 and 12. It has, and I'm just picking, it has 6 and 8. So it doesn't matter how you start, but 48 does have factors. It is not prime. So for example, 48 has 6 and 8. Now 6 is not prime either. 6 has 2 and 3. Now 2 and 3 are prime. That's done. 8 is not prime. It has 2 and 4. But 4 is still not prime. 4 has factors of 2 and 2. Now everything is represented with prime factors. So we have 2, 3, 2, 2, and 2. And we said a lot of 2's there, didn't we? So how many 2's does 48 have? 1, 2, 3, 4. And we already said that 4 factors of 2 is equal to 16. The 3 is, let's say, an extra factor. So this gives us the 4th root of 16 times 3. And the 4th root of 16 is 2. And what is left and cannot be simplified is the 4th root of 3. I have 2 questions for you to do here. So simplify the square root, be conscious of your root, of 40. And then simplify again the square root of x to the 4th times y to the 5th. The next property that we're going to look at is the quotient property. Remember, quotient means division. So if we look at the first example, we have the square root of c to the 7th over 25. So what we can do here using our quotient property is actually separate. So this is equal to the square root of c to the 7th over the square root of 25. And for the denominator, that simplifies to be 5. So now what we want to work with is the square root of c to the 7th. Now one of the ways we can understand this, because our root is 2, we can think about the highest factor of c that we have that is even, and that would be c to the 6th. But then we have one additional factor. Now our root is 2, so our root is 2, and our highest even power is 6. So we can think about the fact that our root of 2 goes into our power of 6 3 times. And we have one factor of c left over. Again, our root of 2 goes into our power of 7 3 times, but with one remaining. We'll practice more with this. Question number 6, we have a lot going on here. First, we have cubed roots, so we need to be conscious. This is a cubed root divided by a cubed root. So we can make this as a cubed root of one big fraction. So this is the cubed root of 625 times c squared times d to the 10th divided by 5 times c to the 5th times d. And now we're going to simplify. 625 is divisible by 5, and that leaves us with 125 in the numerator. Now notice the powers of c. We have 2 factors of c in the numerator, but 5 in the denominator. So the denominator has 3 more factors of c as compared to the numerator. And then for d in the denominator has an implied exponent of 1, and subtracting to simplify leaves us with d to the 9th. And now, taking the cubed root of each piece, the cubed root of 125 is 5, because 5 cubed is 125. The cubed root of d to the 9th is d cubed, because d to the 9 divided by 3 is d cubed. And this is our third time seeing this. The cubed root of c this time to the 3rd power leaves us with just c. So these were just some side notes for you, and this one is done. You have 2 questions. Question 3, simplify the cubed root of z to the 5th divided by 8. Simplify the square root of 2 times x cubed divided by the square root of 32 times x.